This lecture, we're going to talk just a little bit about Saint-Venant's principle. Saint-Venant was a French engineer in the 1800s, the early to mid-1800s, and he studied material behavior and among other things. And when I say he was an engineer, that is maybe selling him a little bit short. He not only was an engineer, but he was a mechanician. He studied how materials and structures behave under loads, but also a mathematician. So he had his hands on a lot of things, fluid flow as well as solid mechanics. And the principle that's named after him, to kind of paraphrase this, since we've been talking about axial loading, we've represented axial loading on a bar in tension by a point force that acts on our bar. But there's lots of other ways that we can develop axial loading situations. We can't really have a point force. We have to distribute some load over some area in order to get that axial force applied to something. And so many of these axial loading cases that don't look exactly like a single axial point force in the middle of a bar can be approximated by a single axial force. And to kind of paraphrase what's going on here is we can say that a short distance away from where the load is applied, the stress distribution becomes uniform. And he was able to do some mathematics, and people since then have done some, and they've been able to show that any disturbances in the stress fields where the contact forces are applied die away as exponentials. So we were talking about axial loading. I'm just going to show a bar in compression. And this is our representation of axial loading. We have a force in the middle. And we know if we were to cut this off over here, we've said that we would get a uniform stress distribution at that level. So there's my equivalent force, and here's my uniform stress distribution. And we would say that that has the same height, and that stress would be equal to that force divided by the cross-sectional area. Of course, if we were to apply a compressive force, we may have, instead of a single point load in the middle, we may put a big weight over the top of it. And so there may be a portion of this bar where that load is applied. So maybe it's only acting over a small bit of this cross-sectional area. If we're using a testing machine, we may grip the sample and put it in compression. So in that case, using the same bar I've been sketching, we might apply some forces on the outside surface area all the way around this bar, and that would be some sort of load distribution that goes around the outside edge. If in all of these cases the equivalent force is equal to the same F, a short distance away from where the load is applied, and in practical terms for a round bar like this may be 3 to 5 diameters of the bar, short distance away, all of these different loading cases give us the same uniform stress distribution. So for us, we don't have to be so interested in exactly how that load is applied. If you look at a bridge or look at some other type of structures, you'll see lots of bolt patterns in the bridges. The stress distribution near those bolt patterns can be very complicated. But if that transmits an axial force a little bit away from where that bolt pattern is, we can get a more uniform stress distribution, and we can use our basic formula for stress. Sigma is equal to F over A. This will also work later for other types of basic stress formulas that we come up with. It's just that we've only talked about sigma is equal to F over A at this point. There's some practical applications to this when it comes to designing test specimens. And if you take a mechanics materials laboratory course, you'll probably do a tensile test on a material. It's kind of a poor sketch of a tensile specimen, but that's the basic idea. And if you notice, this has a shape that's known as a dog bone type specimen. It's a little bit wider on the ends than it is in the central portion. In the central portion is where we're going to take our measurements for our change in length from our extensometer. But around this area is where we would grip it in the testing machine. Because the testing machine grips can bite into the surface of our specimen, we design the ends to be a little bit wider. The idea being when we get away from the stress disturbances from where it's gripped, we get away from the stress disturbance where we have what's called a stress concentration. We'll talk about those later in the semester. And we go past that a little bit and we get to our uniform stress distribution. We still need to have axial loading, but under those conditions, we can be reasonably assured that we'll have a uniform stress distribution. Okay, so it has a couple of implications. You get a uniform stress distribution, but where you apply the load, you may want to make it a little bit more substantial. You'll also see this kind of design manifest itself in connecting rods and engines. In a connecting rod, you have kind of a top portion that's bolted together. It's kind of beefed up, but then it gets skinnier in the central portion, and it comes down to another hole down here, and you'll often see maybe some reinforcing done here at these transitions and so forth. So you're putting material where you need it, but you're avoiding putting extra material where you don't need it, because in the middle of that connecting rod, you do have a more uniform stress distribution if you have a nice axial load. So now, although we won't make a big deal about Saint-Venant's principle from the rest of the semester and the rest of the lectures here, we will just kind of automatically use it without stating it in much detail. So it is a very important concept to understand, and it's usually not brought up too often, but it's good to keep this in mind throughout the entire course.